Hi, folks. I'm back. Just spent like hours talking to different IT folks and whatnot. I figured out how to turn off the notification sounds. And the bottom line is the guy said I have to reboot my computer and my iPad, and then those notifications would stop, and they did. So I think I got them to stop. So I'm going to record this lecture using Zoom just to sort of make sure that I can go through the motions and that it all works. So I'm going to sort of do it just like I would have done it. Like I wanted to do it this morning, and when it did not work. Okay, so I'm recording now. So now what I'm going to do is share my screen, click on the iPad, and now I'm going to do the mirror trick. Click on that. It all looks good. Now let's see if I can write. Oh yeah, it writes. Yay. Okay. So all right. So I will begin now and do the lecture. So I'll just start from the beginning. So we're going to be talking about solid state physics. I'm not going to go over the syllabus and all that. So you guys can look at that and ask me questions if you have any. But let's just start with the topic of the course, which is solid state physics. So solid state physics is the study of groups of atoms. When you take a bunch of atoms and stick them together into a solid, that's solid state physics, is the study of that. And there's many different types of solids. Obviously, there's many types. We can have crystals, insulators, metals. We can have disordered material. We can have molecules, etc. And so really in this class, we're going to focus on crystals. And we're going to also focus on crystals, thinking about their insulating and metallic behavior and other behavior, their phonons and vibrations. But we're not going to be talking about disordered material. We're not going to be talking about molecules, really. I mean, I might mention molecules, but that's just, we're just not going to talk about that. Okay. And so, so let's see. So since we're talking about solid state and as I mentioned before this morning, when we do solid state physics, it also can be thought of as a combination of, basically we're looking at the quantum mechanics, we're combining it with stat mech, and we're combining it with a little bit of chemistry, and that together is equal to solid state physics. That's what solid state physics is. But it's tricky because what we really are doing is we're looking at at all of this behavior for many particles, many atoms, many electrons. And so when you have a system of many atoms, many electrons, and then you start to consider the quantum mechanics plus the statistical mechanics and the chemistry of it all, that is solid state physics. And it's a big topic. It's a huge topic. And so where to begin? And so a good place to begin is at the beginning. A good place to make the beginning is to consider the behavior of a single atom. So because if I have a bunch of atoms, then their behavior is going to reflect the behavior of a single atom, right? I mean, it's not exactly the same, but it'll reflect it. So we really have to understand the behavior of single atoms before we understand solid state physics. So let's remind ourselves atomic physics. And so, of course, the most important atom for us to understand in physics is hydrogen, which is the prototypical atom. And so we remember how hydrogen works. We have the Hamiltonian. We have a nucleus that's positive. We have an electron that goes around it. And then we have a Hamiltonian. And the Hamiltonian is going to be negative h bar squared over 2m. It's going to be the kinetic energy of that electron, which I just wrote. Then this can be the Coulomb attraction of the electron to the proton inside, minus e squared over 4 pi epsilon naught r. And then, of course, we got to get the energy levels, we're going to solve the eigenstate equation, otherwise known as the Schrodinger equation. So we got to solve this equation. And when you solve it, doing all the tricks of solving the Schrodinger equation, then you guys know that you're going to get wave functions. You guys remember this vaguely from some class you took. You're going to get the radial wave function. You're going to get the angular part of the wave function, and there'll be spin too. But let's ignore spin for now. And then you guys know that the energy is negative 13.6 eV divided by n squared. So that should look familiar to you from your 137A class or equivalent that you guys all took somewhere. And so we know that if we change Z, change Z, which is the number of protons and of course the number of electrons. Well, I shouldn't make it a ratio. The number of protons and electrons for a neutral atom, of course. Then you fill it up. Then you fill up the states, and you can get for example, for Z equals 1, then we have one electron in the 1s state, one electron, and so that's the N, that's the L, and that's the number of electrons, right? You guys remember this? And if I have Z equals 2, then of course I would have 1s2, and that's helium, right? Helium. And then one of our favorite atoms of all time is carbon. Z equals 6. We love that. That's how you make ice cream, is out of carbon. And so Z equals 6 is a carbon. And so that's going to be, let me do it a little differently. So that's just going to be carbon, and that's going to be 1s2. And I put parentheses around it because that's a filled shell. 2s2 2p2. So hopefully, guys, that looks familiar. That's the valence configuration of the electrons in carbon. And so if this looks unfamiliar to you, then you need to go review this in your quantum mechanics book to make sure you remember this, because this notation is important for solid state physics. And so here you can see that the unfilled shell is here, right? And then if I had, like, for example, well, that's enough. And so you can see that what's going to happen is that the atoms behave differently. They change, the atomic behavior changes depending on Z. And that kind of makes sense because, and this reflects itself in solids, because for an s orbital, it's like a sphere, and like in a p orbital, they look like that, right? That's going to be the pz, the px, the py. These are the p orbitals. And then we have the d, and then we have the d orbitals, which are going to look different. They got these funky shapes. You guys remember them from your quantum mechanics. We got all these different shapes, right, for the d orbitals, etc. And so the point is that these the orbitals, the atoms have different behavior because the shapes change. Shapes of orbitals change. And so you can imagine that if I have different atoms filled up to different orbitals, then the solids that are formed then are going to be different because the bonding changes. The bonding geometry changes because the shapes of the orbitals change. And so that, I think that's kind of intuitive. And so in this class, that's going to be really important. And so if we start, so what we can do is we can start connecting up. So if we connect up atoms into arrays or networks, however you want to call it, really what we want to call it is crystals, then you start getting a lot of behavior that's different from just an individual atom. So let's connect the atoms up into an array. And here's an example. Here's an array of, say, a square, call it cubic array. And you can see that one of the properties that's going to happen is that the atoms in this array, they can vibrate. So you can get vibrations of the entire array, which we call phonons. And we'll study these in great detail, but I just want to sort of just point them out here at the beginning. So I could have a mode. We get collective modes. For example, I could have some normal mode, like in classical physics, you have normal modes of particles all connected together, because we can think of these atoms as connected by springs. I'm drawing in some springs now. I'm not going to draw them all, but those are springs. So the atoms are connected by springs. And then there's other, and so these are, so this is a collective property of the crystal. Another collective property of the crystal is that the electrons can hop around. And that's a really big deal. So we can have, I can have an electron jumping from one site to another. Throughout the crystal, electrons can hop around. So I'll call that electron hopping. And that's quantum mechanical. And so, so that behavior of the electrons jumping from one atom to the other quantum mechanically leads to a lot of interesting behavior. So that leads to electronic structure and band structure. And then, of course, another, and that's a collective property, because the way they hop around is going to depend on how the atoms are arranged in the crystal. And then another kind of collective behavior. So I'll call this collective behavior. Another kind of collective behavior is magnetism, because I can have the atoms, each of the atoms can be magnetic, and I can have spin, and I can have different spin patterns. Like those top ones can go spin up, and these ones can be spin down, and it can alternate. So this is a type of antiferromagnet that I just drew. And so this is what we call magnetism. And that's also a collective behavior, which depends on all the atoms in the crystal and the symmetry of the crystal, etc. And then you can have other many body effects. Which are collective effects due to the fact that you have lots of electrons living inside a crystal. And these kinds of collective effects can lead to, for example, superconductivity. When the electrons pair up into Cooper pairs, CDWs, charge density waves, plasmons. We'll be talking about some of this stuff, not all of them. Spin waves. And so there's all kinds of different effects that can occur. And so the study of solid state physics is the study of all of this types of behavior. And so, so in this class, what we're really going to focus on is first, we're going to look at this behavior. We want to talk about the structure of crystals and how they vibrate. So that will be the first topic. And then the second topic we'll then move and talk about what the electrons do. And both of these topics involve quantum mechanics and stat mech, although there's more quantum mechanics in the electron hopping part. But in the vibrations and phonons, there's also quantum mechanics there, but there's a lot of, it's more stat mechy, I think. But both of them have quantum mechanics and stat mech. So, but we'll do the vibrational properties first, and then the electronic properties next. And this, I mean, when I say, I'm talking about over a period of weeks. So let's talk about, okay, so we want to understand how, okay, so let's say we want to do this first topic, how do crystals vibrate? What are the vibrational properties of crystals? Well, first we have to ask ourselves, how do we even get a crystal? Why do we get a crystal? Why do we even get crystals? Why get a crystal? And the reason, of course, is because atoms are sticky. They stick to each other. Atoms are sticky. That's the answer. And why are they sticky? Because they bond. They like to bond. Because the bonding is often a lower energy state. Bonding provides lower energy. That's why. So this is something then, so in order to understand solid state physics, it's useful to think a little bit about bonding. So let's talk about bonding. Why atoms stick together, because this is sort of fundamental. This is like why we have crystals at all. And it helps to understand crystals, I think, to understand bonding. So let's talk about bonding. Now, when you talk about bonding, that's a chemistry thing. And so this is going to be a moment in time when we are going to be like chemists. We're going to talk about chemistry, all right? Because like I said, solid state physics is the combination. It's the combination of quantum mechanics, stat mech, and chemistry. So right now, let's talk a little bit about chemistry because that's where bonding comes from. And so what kind of bonding can we have? And so some of you are chemists. Probably most of you are not, but some of you are. And so those who are chemists or who have taken chemistry know that bonding, there are many types of bonding, and it's kind of a confusing mess, to be honest. The first type that we'll talk about is covalent bonding. The second type is van der Waals. Spell it out. Van der Waals. Third type is ionic. Fourth type is metallic. And so those are the ones that we will talk about. There's other types, like you could talk about coordination bonding. There's all kinds of bonding in chemistry and combinations of the bonding, and it's quite complicated, and that's why chemistry is a whole nother field. But here we'll talk about just these four different types of bonding, because all of these are very important in solid state physics. And so that's why it's worth just talking a little bit about this on the first day of class. So let's talk about covalent bonding. And so let's talk about why covalent bonds form. And so right now, let's just do chemistry. So let's talk about the hydrogen, two hydrogen atoms, and how they form a molecule called H2, which is otherwise known as hydrogen. So when you get hydrogen gas, it's actually molecules of H2. That's not ionized hydrogen. You have to do a lot of work to ionize. I'm sorry, it's not atomic hydrogen. You actually have to do a lot of work to turn hydrogen gas into atomic hydrogen. It's actually quite difficult. Okay, and so H2 is a molecule, which we can write like this. This is the way chemists would write it, where this dashed line denotes the bond. But another way to write it also is you could do it like this, because you can write two little dots there. And so those are two electrons in the bond. And so let's ask ourselves, why would two hydrogen atoms stick together and form a molecule of hydrogen called H2? And so this is the simplest example of covalent bonding. So let's work through this a little bit. I think it's worth it. And the reason why I do this in this class is because most physicists really don't really see a quantum mechanical treatment of bonding, and that every chemist sees it, but most physicists are surprisingly ignorant of chemistry, most of them at least, not all. And so I just want to remind you how bonding works. So let's look at covalent bonding from a quantum mechanical picture. And so the simplest way to think about it is to consider 2 protons plus 1 electron. So let's look at this. So we call this the single electron picture. And so let's look at the state of 1 electron in the vicinity of 2 protons. And that will help us to understand covalent bonding and why these 2 hydrogens bond. So let's draw it out. So let's draw it here. And this is, I'll call this atom A, but these are hydrogen atoms, and I'll call this atom B, positively charged. Those are the nuclei, the protons. And they're separated by a vector I'll call R, big R. And then let's put a little electron somewhere. And so I have a little electron that's right here. And he's negatively charged particle. He's an electron. And he's located from the center of the first atom, he's located at a vector called RA. But if from the center of the other one, he's located at a vector RB. And of course, these are not independent variables because we know that RB is equal to RA minus R. So if you know RA and R, big R, then you know RB. So, but the point is that we have 1 electron which is shared between these 2 different nuclei. And so we want to know what are the states? What is the ground state? What are the states? And so to do that, then we need to know, we need to solve the Schrodinger equation. So let's do that. Let's solve the Schrodinger equation. And so the Schrodinger equation, we have to write the Hamiltonian. That comes first. And so we know the Hamiltonian is going to be, it's going to be the kinetic energy of the electron, right? And it's going to be the electron is going to be attached. It's going to be attracted to nuclei, the first nuclei, 4 pi epsilon naught RA. But it's also going to be attracted to the second guy, negative E squared over 4 pi epsilon naught RB. And then, of course, the 2 nuclei will repel each other, Z squared. Oh, let's not use Z. They repel each other, E squared over 4 pi epsilon naught big R. All right, that's the Coulomb repulsion between the 2 nuclei. But we can, but we'll just say that the nuclei are fixed. Nuclei are fixed. So then we can ignore this. We can ignore the motion. We can ignore that because let's just worry about the electron. So then we want to solve the Schrodinger equation, which is H psi equals E psi, right? But it turns out it's really hard. That's a hard problem, to actually solve it correctly. I think I saw it done in some paper, but it's really complicated. It's super hard, at least in my opinion. And so let's do something else. So let's see. So big R is a constant. The separation between the 2 protons. Let me just label these guys proton. And so let's not solve the Schrodinger equation. Let's do something simpler. Let's use the variational principle. And this is what chemists do. And physicists do it too for a lot of things. There's no shame in using the variational principle. And so what we're going to do is we're going to, for the variational principle, we're just going to assume, we're going to make an assumption about the wave function. We're going to assume that the wave function is equal to an LCAO. And at this point, I would say, does anyone know what that stands for? And then I would want hopefully somebody to shout out, that stands for linear combination of atomic orbitals. LCAO, linear combination of atomic orbitals. And so what that means then is that we start with a wave function psi A of R A and another atomic wave function located centered at proton B, which is psi B. So we assume that we know these two states where these are atomic states, like hydrogen wave functions, hydrogen orbitals. So let's start with these known states. These are known. So let's start with these two known states, and then let's assume that the wave function that we're looking for, psi, which is the wave function of the electron, which is really only a function of our. Well, I'm not going to get confused about that. Let's not get too caught up in that. We're going to call that psi. We're going to assume that psi is a linear combination where I have some constant Ca times psi A of Ra plus Cb, a constant times psi B, which is a function of Rb. But remember that there's only one variable really, since Rb is equal to Ra minus big R. So there's really, the only variable really is Ra, okay? And that's the location of the electron, in case you're forgetting. I know we're like getting all caught up in the math and everything, but so these functions are known. These are just atomic orbitals, but the constants Ca and Cb are the variational constants, the variational parameters. And so using I'm hoping that you all have seen the variational principle. It's something that's supposed to be covered in your first year quantum mechanics course. So I'm assuming you all have seen it. Although, of course, some of you might not have seen it because it slipped through the cracks and your professor did not cover it wherever the heck you learned quantum mechanics. And that's okay, because lots of things fall through the cracks, but it just means that you're going to have to go look it up. Okay. So if you've never heard of it, then go look it up, the treatment of the variational principle, and remind your, and learn it. It's not hard. It's easy to learn. But I'm going to assume from in this discussion that you have learned it and that you know it. So Ca and Cb are variational parameters. And so we're going to minimize the energy, the variational energy from these parameters. And that's going to give us the bonding. That's going to explain bonding. So let's do the variational principle. So for the variational principle, what we do is we say that the energy, the ground state energy, the lowest energy, is equal to basically the variational principle. What we do, the trick of the variational principle, is to say that the energy is equal to the expectation value of the Hamiltonian using the variational wave function, which is equal to, this is how we do it. We say psi h psi over, and then you got to make sure that the wave function is normalized. You just divide it by the overlap of psi into psi. And if you have forgotten Bronquet notation, I'll just remind you that what that thing on top is just the integral of psi star h psi d cubed Ra divided by the integral of psi star psi d cubed RA. Okay. And so then what I'm going to do is let's define some integrals. I don't want to actually do the integrals, but let's just define them. Let's define H A is defined as the integral of psi star A H psi A d cubed R and similarly, of course, HBB is equal to the integral of psi star B H psi B d cubed R. And by symmetry, you expect that to be the same as HAA. So I'm just defining some integrals right now. And there's a reason why I'm doing it, as you'll see in a moment. Let's define HAB as the integral of psi star A Hamiltonian. And the Hamiltonian is defined up above. Psi B d cubed R and S is equal to the integral of psi A star psi B. This is really the overlap integral S d cubed R. And if I make these definitions, then this thing here, which is the energy, is going to be, I can write it, if you kind of grind through a little bit of algebra, then you can see that it's equal to C squared A H A plus C squared B. And it's really easy to do this, just a little bit of algebra, and you guys should do the algebra on your own. It's not hard, it's just a little tedious. 2 times C A C B H A B divided by CA squared plus CB squared plus 2CA CB times S. And so that's what the energy is, assuming that variational form of the wave function up here, right? And so now using the logic of the variational principle, what we do next is we minimize. And I would actually ask you at this point, what is the logic of the variational principle? What do you do? And what you should answer to me is you minimize the energy with respect to, that's what WRT means, with respect to CA and CB. Okay. I'm just making sure that this is all being recorded. I hope I pressed record. I think I did. Okay. And so then we, what we do is we got to do this. So we got to take the derivative of that expression with respect to CA, and we got to set it equal to 0, because that's going to allow us to find the minimum CA. But we got two parameters, CA and CB, because there's two orbitals. So now we got to take the derivative with respect to CB. Set that equal to 0. So now we have two equations. This leads to two equations. And that makes sense because we have two unknowns. And the unknowns are CA and CB. Those parameters. So that's what we must find. That's the whole point. That's what we're trying to find. That's the whole point of all this. I should have said that before. So from those two equations, from this minimization scheme, we get two equations, and those equations are CA, and it's easy to do. Just take the derivative, set equals 0, and you get this immediately. We get this expression plus CB times HAB minus ES equals 0. So that's just the first derivative of CA equals 0. And then we take the first derivative with respect to CB, and we get this. Then the next equation is CA HAB minus ES plus CB times HBB minus E equals 0. Now, the reason I wrote it like that is because that should suggest to you a matrix formulation, because when you look at that, it looks like a matrix. Looks like a matrix equation. So let's just turn it into a matrix equation. It's really easy to see that those two equations can be written in matrix form like this. So we have a matrix, HAA minus E, HAB minus ES. And then here I have HAB minus ES and HBB minus E times this CA, CB. So I define this new type of vector equals 0. And so then you know that if I have a matrix times a vector equals 0, then I know that, of course, the determinant of that matrix has to equal 0, because that's something you know from linear algebra. And so then I do it. So then I take the determinant of this. So then I take the determinant of this thing. So this times this minus this times this equals 0. And that leads to a single equation, which is HAA minus E times HBB minus E minus HAB minus ES squared equals 0. And so that's a quadratic equation. And then what we do is we solve for E, and we get 2 solutions because it's quadratic. 2 solutions. I'll call them E plus and E minus. One is big, one is little. Although the bigger one is actually E minus, so maybe the notation is not great, but it is what it is. Okay, so here's the solutions of the 2 solutions. I'm going to have E minus is equal to HAA minus HAB divided by 1 minus S. And then so that's an eigenvalue. And so then if I plug that back in, if I plug back into the matrix equation, which was this equation, CA, CB equals 0. If I plug this into that, then I can solve for CA and CB, and I can see that CA equals minus CB, and that's easy to do. I'm not going to do it. That's some algebra, but this is very typical eigenvalue problem. Once you find the eigen, so once you find the eigenvalue from this equation, which we call the characteristic equation, then we plug that back into the matrix and we get the eigenstate. We'll call this the eigenstate, which is that vector, which is basically the values of CA and CB that correspond to that energy. And then we see that CA equals minus CB. And so from this, we then see from the definition of psi, we see then, because psi is equal to CA times the 1 orbital times CB times a second orbital, we see that psi minus can be written as psi A minus psi B, where I've just divided out the values of psi. I just divided everything by Ca. I can say up to a constant, up to a constant. And then I can see that there's another solution, which is E plus, the higher energy, I'm sorry, the lower energy solution, and that E plus. So let's put circles around these solutions. E plus is equal to H A plus H A B divided by 1 plus S. And so that's a lower energy solution, usually. And then this then leads to a value of, then you plug it back in, plug it into the matrix, Ca, Cb equals 0. And then what you get is that Ca equals Cb for this one. And so that then leads to the solution, the eigenstate, psi plus is equal to psi A plus psi B up to a constant. And so those are the states. That's what we get. And so this one, it turns out, we call the anti-bonding state. And this one we call the bonding state. And I just want you to see that what we've done is these are single particle. Remember what problem we're solving. We're solving this problem from the very beginning. We have 2 protons. Here's the picture. See the diagram. We have 2 protons and 1 electron. That's the problem that we've just solved using the variational principle. And so what this means sort of diagrammatically, I mean, so that's a bunch of equations that I've written down, but it's actually kind of simple. If you're lost in the equations, that's okay. Don't worry, because you can just do it all in pictures. So what the picture that represents all this math is that one atom is here, and I have an electron in it, and then that's one hydrogen atom, and then the other atom is here, the other hydrogen atom, and the electrons are both sitting at the same energy in both those atoms. But then when I bring them close together and the electron, and now if I can have an electron that's shared between them, then I see I get a splitting of states. And I get this is my E minus state. And this is my E plus state. And I can see that this corresponds to psi minus, which is going to be 1 psi A minus psi B, which looks like this. It's going to be, let's see, let's make this drawing a little better. So it's going to be, I got the 2 atoms there and there. And so it's going to be like, it's going to look like this. So that's going to be like psi A minus psi B. So that's going to be what it looks like. Psi A psi minus equals psi A minus psi B, because that's what it really looks like. And then for psi plus, it's going to look like, and these dots, this is where the atoms are located. It's going to look like this one, and then they're going to overlap. So it's going to sort of look like this, a big blob. And so this is psi plus equals psi A plus psi B. And so here we have no electrons in middle. We have a node. And here the electrons are in the middle, can be in the middle. Electrons are in middle. And so, and then this splitting energy, we call this delta E. And so that's the bonding energy. So what we can say is that delta E is the bonding energy. Because if we have two electrons, then what happens is these two electrons. So because the idea is that if I put two electrons now into the system, I have these two states, the high energy state, psi minus, and this is psi plus. But these two electrons are both going to go to this low energy state. So they're both going to go down, see? The electrons are going to go into the bonding state. And so it's a lower energy state. And we calculated it because it's all calculated above, E plus and E minus. So it's all these expressions that we just calculated. Okay, so that's the theory of covalent bonding. And I'm sorry to drag you through all that, but I just want you to see it at least once in your life. I mean, maybe some of you have already seen this. I'm curious how many have seen this and how many have not. But this is the basic theory of covalent bonding. And this explains about 94% of all chemistry, what we just did. And so, but it can get a little tricky, you know? It can get a little tricky because how atoms bond can depend on which orbitals are doing the bonding. So, for example, some materials that do a lot of covalent bonding, some materials that are held together covalently, examples of that are carbon, silicon, and germanium. And to understand what is going on for these materials, it can be a little tricky because for carbon, we look at the valence configuration and we have 2s2, 2p2, 4 electrons there, the valence electrons. And for silicon, we have, it's further down in that column, 3s2, 3p2, 4 electrons there. And for germanium, we have 4s2 and 4p2. And so you might think that naively you would expect this kind of situation to occur. I have one atom here, let's say of carbon, and another atom of carbon, and you might expect the valence configuration to really look like this. You might expect 2 electrons to be living in the 1s orbital and and then I have 2 p orbitals. And using Hund's rule, you might expect this kind of a thing. So this is what you might expect, that energy level diagram. I'm thinking that this is getting a little confusing. Let's do it like this. Let's call this, and this is P, and this is a carbon atom. And this is meant to be energy in the vertical scale. And these are the p orbitals and the s orbitals. Now, and then you might expect those to do all this bonding stuff that I just described above, but that doesn't really happen. Well, these orbitals look like this. You know, you might have this as a, that's the s orbital, and then this is the, you know, one of the p orbitals. That's like the pz orbital, and this is the px orbital, and this is the py orbital. And so you might expect that it's, you know, these orbitals are all going to do their own separate bonding, but that doesn't really happen because what happens is that in real life, you get hybridization of these orbitals. And what's going to happen is that you're going to get instead, these things are going to form, they're going to hybridize together, and you're going to get this weird thing where it's hard to draw, but I'll draw it anyways. Let's see. The tetrahedron. And so you're going to get like this thing where you're going to get these 4 lobes at the corners of a tetrahedron. So I guess I didn't draw that too well, but this is a tetrahedron. Tetrahedron, four-sided pyramid. You can think of it as a pyramid with a triangular base and three sides above, up high. It's a tetrahedron, and so you're going to get these four orbitals, and those orbitals we call the sp3 orbitals. And so instead of getting this kind of a picture, which you might think of using Hund's rules, you don't get that, but instead you get, where this is S and this is P, instead you get four orbitals that are all the same. And you get the electrons in those four orbitals. I'll just draw them like this. And these are sp3 orbitals. And so then it's the sp3 orbitals. So basically what you think of is the carbon. So this is carbon. So the carbon atom is the orbitals of the carbon really are these, have these four sp3 orbitals that stick out. And it's the sp3 orbitals that bond. So if I have two carbon atoms, one's here and one's here, then it's these sp3 orbitals bond. Let me try to draw this better. So this is carbon here, and this is carbon here. And so this is one sp3 orbital, and this is another sp3 orbital. And so these are the things that bond, and we call it sigma bonding. And so that's how you get diamond, silicon, and germanium. It's these sp3 bonds that these tetrahedra that bond together. So that's a little bit not really intuitive. I realize that, but I still think it's worth talking about because, that's what really happens. And so I just wanted to give you some sense of that. And then there's other ways that our orbitals can form too. So there's another type of hybridization is that you can get sp2 bonding. And so for sp2 bonding, then what happens is that you get the s orbital and the px orbital and the py orbital. And they squish together. And there's the pz orbital. And they squish together into this, and you end up getting, it's really a triangular arrangement. You now, instead of a tetrahedron, you get three lobes that match the corners of a triangle in the plane. And then you still have the pz orbital out of the plane. So this is in the plane, and this is out of plane. And so these are the sp2 orbitals. And there are three of them. Three. Because each of these lobes is an sp2 orbital. And so you can get bonding of the sp2 orbitals, and that leads, so bonding of those sp2 orbitals the sigma bonding of the sp2 orbitals leads to structures that have not tetrahedral symmetry, but they have honeycomb symmetry. So you start getting these hexagons, but now the hexagons form a honeycomb. And so you get this honeycomb bonding because see these are the three sp. So those are each intersection has these three sp2 bonds, sp2 orbitals or bonds. these sp2 bonds from the sp2 orbitals? Well, they're actually sigma bonds made out of sp2 orbitals. Sigma bonds from sp2 orbitals. And that's important because that leads to materials such as graphite, graphene, because every intersection here is a carbon atom. And this leads to, you can get nanotubes, buckyballs, etc. So that's another kind of bonding, and these are all covalent bonds that form due to the quantum mechanics that we just described. Okay, so that's all I want to say about covalent bonds, just to give you kind of like a quick introduction. But then there are certain materials, but there's something important about covalent bonds. Like, check it out. Let's say I have two hydrogen atoms, and I have one electron here and one electron here, where this vertical scale is energy. They're at the same energy because they're hydrogen atoms, H and H. And then let's say they hybridize according to the quantum mechanics that we derived a few moments ago. And here I have the E minus, the anti-bonding level, and the E plus, the bonding level. Now, if I have two electrons, then these two electrons go here and here, and you can see that there's a lowering of energy. Clearly, the system has lowered in energy by 2 delta. You can just see that. But what if instead of hydrogen, I had started with H minus and had 2 electrons, and H minus and I had 2 electrons? Well, maybe I'll do it differently. Maybe I'll do a different picture so I can, make it more clear. So now, but what on the other hand, if I do this, if I start with H minus, so this is a bond because we get a lowering of energy. But what if I have H minus and H minus, where I have 2 electrons now and 2 electrons? Now, what if I bring those guys together? Because now I have filled. This is really sort of like helium, but it's not. It's ionized hydrogen. Well, actually, no. Let's just do helium. That's a good idea. Let's just call this helium, and rather than ionized hydrogen. So what if I had brought helium? Helium. So not, because helium has 2 electrons. And now if I try to bond helium, then the same quantum mechanics happens. It's the same. Quantum mechanics is the same. I get E plus, E minus, just the same as hydrogen. But now there's a difference. The difference is that now I have 4 electrons. So, and you know, from the Pauli exclusion principle, only 2 electrons can go in one orbital because they're going to have spin up and spin down, spin up and spin down. So I put 2 electrons here, but now I have to put 2 electrons here in this high energy state, the antibonding state. And so as you can see, it's up here above, we got bonding because it's lower energy. But here we see that there's no bonding because there's no lowering of the energy. Because energy is not lower, energy not lower. And I'm talking about the total energy when you add it all up, because these 2 electrons are clearly at lower energy, but these 2 electrons are at higher energy. And so when you add it all up, there's no savings, there's no energy savings. And so if I have filled shell, so the bottom line is that filled shell, meaning their valence shell is filled shell atoms don't covalently bond for this reason that I just showed you. But we can make crystals of filled shell atoms. Like, for example, if I take argon, which is a filled shell atom, argon is a filled shell. It goes from the 1s2 all the way up to the 3p6. It's a filled shell. Then if I take a bunch of argon, then in a gas, if I take it in a gas, It's a gas at room temperature. But if I freeze it, make it really cold, it forms a crystal. Where they form a crystal, not a square lattice. It's a different kind of lattice, but whatever. It's a crystal at very low temperatures. I forget what temperature, 20 degrees Kelvin. I forget what it is, but it's a crystal at very low temperature. Now, that means that argon is bonding. So that tells us that argon bonds at low temperature because it forms a crystal. I mean, you can do the experiment yourself. Stick some argon into liquid helium and you'll get it and it'll freeze. Argon bonds at low temperatures. So then how? What kind of bonding mechanism is that? It's not covalent. So what is it? Well, I'll tell you. It's van der Waals bonding. Van der Waals. Van der Waals. Van der Waals bonding. And van der Waals bonding is super important. It happens a lot. And the reason that van der Waals bonding is really important is because van der Waals bonding happens for if I have filled shell neutral objects, atoms, or even molecules or anything, atoms, molecules, solids, then they bond. And this van der Waals bonding, we call it VDW, just because no one likes to write van der Waals. It's too tedious. So then what we do is we get VDW bonding. So what is VDW bonding, van der Waals bonding, and how does it work for filled shell neutral atoms? How do they bond? It's not obvious what the mechanism is. So let's talk about it. So let's consider the mechanism, the van der Waals bonding mechanism. So the way it works is that the way to understand it is that you have this, you have one atom here, and I have another atom here. And let's say that they're separated once again by this vector R. Now, this atom, let's just think of it as two hydrogen atoms or helium. Let's think of it as two helium atoms. So let's consider one of the electrons in helium. Oh, shoot. And so the electron is here in one atom. And the center is the proton. And so I'll call that R1. And this is plus E, because that's the proton. And in the other one, I'm going to have the electron somewhere else. E minus, and this I'll call R2. And I'll call this plus E. Okay, so this is two atoms. I got two atoms here. And the point is that when I look at those two atoms, I notice that each atom has a dipole. It's a dipole mechanism, electronic dipole, because this is a electronic dipole, P1. And this is electronic dipole, P2. Because you guys remember dipole, like the definition of a dipole that you learned in electricity and magnetism is that the dipole moment of any system of charge is equal to, you just have to sum up all the charge. And you just sum up Qi times the position of each charge. And so you can see that, so then if I have minus E and plus E, then I'm going to have a dipole, which is going to be pointing from the minus to the plus. And that'll be the P. Okay, and you can see it just by doing it. You can just calculate this dipole, and you see that that's the dipole. And so each of these atoms has a dipole made up from the electron plus the nucleus. I'm doing this for just one electron, one proton, but even if you have many electrons, it's the same physics. And so what happens is the dipoles attract each other. Dipoles attract. And the way to think of that is not attack, attract. Dipoles don't attack. Dipoles attract. And so the way to think about it is like this. If I have a dipole like that up and another dipole like that down, I'll call that P1 and P2, then this is going to be that I have plus charge here, minus charge here, plus charge here, minus charge here. And so you can see how these two dipoles are going to attract to each other. Like these pluses and minuses are going to attract, and these pluses and minuses are going to attract. You see? So when you if I put the dipoles in the same direction, they don't attract, but if I put them in opposite directions, they attract. So dipoles attract. And so how does that bond? So that leads to a bonding mechanism. But to calculate the bonding, then what you really need to do is calculate the energy. For example, what is delta, the change in energy due to the bonding, change in energy? Now, due to bonding. And now we did this already for the covalent bonding. We actually calculated what this delta is, the change in energy. We use quantum mechanics, and you can do that again here. You can do the quantum mechanics of two atoms, of two filled shell atoms. But it's work, it's a bunch of work, and I don't feel like doing it. But if you feel like looking at it, it is done in the book by Boehm. It's a quantum mechanics text book. Very famous. Very good. I love it. It's one of my very favorites. It's like quantum mechanics. Just look it up, quantum mechanics, Boehm, and Google it. You'll find it. It's a great textbook. Lectures on quantum mechanics by Boehm. And he solves this problem. You can see all the details there. I'm not going to do it. But there's a really simple way of looking at it. Very simple picture. And that simple picture is the following. Let's consider, we know that the E field of a dipole, and you guys all know this because you learned it in some class once upon a time, it's proportional. It falls off as 1 over r cubed. You know that as you go, because because it's this thing. Here's the P, the dipole moment, and it has an electric field that looks like this. And that electric field, it looks like this. You guys have all seen it. This is the electric field of an electric dipole. And this E field falls off as 1 over r cubed. So you know that. And something else that you know, or maybe you don't know, but we'll discuss it more in this class, but you might have learned it in another class, is this thing called polarization. So polarization is induced dipole. So the induced dipole in a material, the polarization equals the induced dipole, I'll call it P induced, is proportional to the electric field. So if I have a material and I put it into an electric field, then it polarizes, and the polarization is an induced dipole. So the bottom line is this. It's really quite cute. The idea is that if I have one dipole here, then this dipole, if I have another atom here, then this dipole field will induce a dipole, but the dipole now will be in the other direction because the E field is down at that point. So I'll call this P1, and I'll call this P induced in the other atom. And I know that P induced is proportional to E. And so then I can ask myself, what's the energy of that dipole? And I can see that the energy of that induced dipole, the induced energy, now I'm talking about energy, is equal to, for a dipole in an electric field, you know, it's minus electric field dot P. And so if the electric field goes as 1 over r cubed, the separation between the two atoms, and if the induced dipole is proportional to the electric field, but the electric field is also proportional to 1 over r cubed, then you can see that the energy, the induced energy, is proportional to negative 1 over r to the 6th, because it's 1 over r cubed times 1 over r cubed. And that's it. That's energy. So not electric field, energy. And so that's a reduction of energy. So the induced dipole reduces the energy of the system by E induced equals some constant times 1 over r to the 6th. I'll put a negative sign there. I'll call it negative sign. So it's negative A over r to the 6th. Okay, so that's that, and so that's the bonding. So the van der Waals bonding falls off. It's very weak. Is weak bonding, and it falls off as 1 over r6. So as materials, so if I take two neutral atoms like argon and I bring them together, they're going to bond via this induced dipole business, but it's a weak bonding and it falls off very quickly as I pull them apart. And that's van der Waals bonding. And it's very important. Like, for example, that's why the layers of graphite hold together, is that van der Waals bonding. And so, but something else to remember is that if I bring two, let's say, argon atoms together, then I'm going to get attraction. Van der Waals attraction, which goes as 1 over r to the 6th. But if I bring them too close, then what happens is, if they get too close, argon, if the orbitals, if they're too close, if they get too close, then what happens is they repel. Too close, then they repel. And that repulsion is, you can think of that as they repel. And there's different ways of thinking about that. One way is people call that polar repulsion. Because now the orbitals, I have electrons in the same orbital, which are trying to now coexist in the same region of space. And so they have to repel. That's polar repulsion. Or you can think of it as just like an anti-bonding interaction, because now what's happening is that now I'm forming bonding states due to quantum mechanics. And now the electrons are pouring into these bonding orbitals, but they're going into the very high energy bonding orbitals. High energy. What's happening is that high energy anti-bonding orbitals are being filled. either way you think about it, it's okay. The point is that you're getting repulsion. And so the word that I will use here is Pauli repulsion, because that's a word that a lot of people use, Pauli repulsion. And this Pauli repulsion is highly repulsive, and it goes as 1 over r to the 12th. And maybe I should use big R, because now we're talking about the distance between the atoms, big R, 1 over r to the 12th. And the van der Waals attraction is 1 over big R to the 6th. And the Pauli repulsion goes as 1 over r to the 12th. So you can see that the repulsion is very short range, but very strong. Because you can see that as R gets big, it's going to fall off very quickly. But by the same token, as R gets small, it's going to increase very quickly. So it's very short range and very strong. And so then so the total interaction between two filled shell argon atoms, total interaction is going to be this. So I can say that the total interaction between atom 1 and atom 2, U for energy, as a function of distance between the two atoms, is going to be minus A over r to the 6th plus B over r to the 12th, where A and B are sort of constants that are positive constants. So this is telling you that this is the attractive van der Waals, and this is the repulsive Pauli. And I just want to say that, this 1 over r to the 12th behavior, I have actually never seen it derived, and I can't even find it derived in the book. Everybody just uses it. It's everywhere. Everyone uses it, but I have actually never seen it derived. So if you ever can see a derivation of it, let me know. I'd love to see it, because I've been looking for it for more than a decade. Okay. And so that's the interaction. And so if I have a collection of crystals, so if I have a crystal of argon, where I have like a bunch of argon atoms, let's say, and I just bring them together, if that's argon, where this is argon 1, 2, 3, 4, 5, and I have some origin, and that's R1, and that's R2, and that's R4, they're all located at these vectors. And if that's the case, then I can add up the energy, because I could say, what I could do is I could say, I could look at one argon atom and I could say, what's the energy, the U total for one atom surrounded by others. And that I could call, I would do this. I would do a sum, and you would do this. You would do a sum of Uij, where I does not equal J. But if I just picked one atom and I just looked at I'm just adding up all the paired interactions. Okay. So let's say that you do that, and that's what you get for one atom, adding up all the paired interactions. But then what I can do is I can then do it for all the atoms, and I can say U total. So if I define this quantity as all the pairing interactions added up, adding up all the pairing interactions, then the U total is equal to, just if I have n atoms, then I can just say it's n times this. I does not equal to J, Uij. But there's a little problem with that because this actually double counts. And to see that, you have to kind of screw around with it a little bit, and you'll see that this is actually double counting if you do that. And you have to think about it for a few minutes, but once you do that, you'll see it is. And so you got to put a 1/2. It exactly double counts. So the total energy is 1/2 times n times this. And you could sort of screw around with it for a few minutes until you see that yourself. It takes a few minutes to figure out, but that's the total energy then, where now Uij of R is equal to minus A over Rij to the 6 plus B over Rij to the 12th. So that's how we can write the energy of a crystal of say argon atoms or atoms that are where there's no covalent bonding. It's just van der Waals and polyrepulsion. And then what we could do is take this, we can minimize the energy of U total with respect to R1, R2, R3, the location of all the atoms. You can do that. And when you do that, then you'll find that this leads you into a crystal shape. That's how crystals form. Because crystals are the minimum energy structure. And so you'll see that the minimum energy structure is a crystal. And it's a certain kind of crystal. We call it an FCC crystal for argon. But there are other types of crystals too. And we'll talk about the different types of crystals in another lecture, not today. But today we're just talking about how crystals form. And so that's van der Waals bonding. And then I will talk about the third type of bonding, which is ionic. And the ionic bonding is what happens when you combine, you guys have all heard of it, I'm sure. You combine electropositive atoms with electronegative atoms, electronegative atom. And so electropositive atoms mean that they have a low ionization potential. And electronegative atoms mean that they have a high electron affinity. And let's remind ourselves what that is. Ionization potential is IP. Electron affinity is EA. And let's remind ourselves what that is. If I have an atom where there's some electron here, then for this electron to jump out, this energy is the ionization potential. But on the same token, if I have that same atom and I add an electron into it, then that electron will come at some energy, and then that electron has a lowering of energy, and that lowering of energy is the electron affinity. Okay, so that's the definition of, and you've probably seen those definitions before. And so the most famous example, of course, is salt. Most famous example of a crystal that forms due to ionic bonding. Most famous ionic bonding example is salt. Table salt, sodium chloride. And you can just sort of see it. It's kind of straightforward to sort of get a gist of what's going on here. Because if I have sodium, which I will just remind you is Z equals 11. And so sodium, the electron configuration of the valence electrons is 1s2, 2s2, 2p6, filled shell, and then 3s1. one electron in that 3s orbital, and the electron affinity, I'm sorry, the ionization potential, electron affinity, how am I going to write this? The energy of ionization, the ionization potential is equal to 5.1 eV, which is low, relatively low. And then I have chlorine, which is, I'll remind you, is equal to 17. And so electrons like to jump off of sodium. That's the ionization potential. And chlorine has this configuration: 1s2, 2s2, 2p6, 3s2, 3p5. And so it likes to suck up electrons, and the electron affinity is 3.6 eV. That's the electron affinity, defined as I showed in that picture above. And so that means that if I take a sodium atom and a chlorine atom, and I put them in proximity, then an electron is going to jump across. And this one will then become plus, and this one will become minus. And if that happens, then there's three energies. There's three energies that we have to think about. Because now, if it's plus and minus, now there's a Coulomb attraction. So I'll call the Coulomb attraction is equal to, I'll call it V attraction is equal to minus 7.9 eV. So that means that if that's a distance, that's just, that number is really easy to come by. That's just Coulomb attraction for a distance of 3 angstroms. Calculate it for yourself and see. So because that's a typical distance in a crystal is 3 angstroms. So if I have a plus and a minus 3 angstroms away, then you work it out. You get about you get about 7.9 electron volts of attraction, negative energy. And so that means that the total amount of energy that I get, that means that the total energy, the change in energy, delta, because if I say the initial energy minus the final energy, or maybe what I should say is, let's do that opposite. Let's say the final energy minus the initial energy is equal to 5.1 eV minus 3.6 eV minus 7.9 EV equals minus 6.4 EV, because that's the energy it took to ionize, the ionization potential to ionize the sodium, and that's the electron affinity, the energy gained of sodium, and that's the electron affinity of chlorine, and that's the Coulomb attraction. So you can see that the system, so that means that the system will gain 6.4 electrons, 6.4 electron volts for if an electron jumps from sodium to chlorine. And so that's quite profitable. That means it's going to happen because that's a big lowering of the energy. So this is a bonding interaction. And so that's the origin of the ionic bond between sodium and chlorine. So the two atoms are bonded by 6.4 electron volts. And so you can start doing things like, so now you can do things like you can have a lattice where now you have, you can have plus and minus and plus and minus and plus and minus, and you could start adding up the energy of a crystal of salt and say, what is the energy of that? So I have a crystal, a salt crystal. And so you can do the same thing, because you can say the energy for one ion, in presence of all the neighbors, in the presence of all others, is equal to the sum of I, for I not equal to the j, of this interaction uij, where uij is just the interaction between them, and the uij is going to be, it depends whether we're talking about which ions we're talking about, but it's between any two ions, it's going to be plus or minus E squared, depending on the sign of the charge of the ions, 4 pi epsilon naught Rij, and that's going to be plus B over Rij to the 12th, because that's going to be the Coulomb attraction. And then that's going to, so if I took a bunch of ions and just put them together, then I could think of the energy like this. That's the Coulomb attraction or repulsion. And then this is the, and of course, this will be the Pauli repulsion. And so using similar kind of reasoning as before, well, first you can just, there's something useful to notice, which is that if I plot this Uij, there's a famous plot, you can see that it looks like this. If I plot Uij versus Rij, you can see that it's repulsive when they're really close, but it's attractive as they get further apart. And then of course there's the minimum energy configuration. So that's where the atoms, that's the distance, that's the preferred Rij is at the bottom of that. And so then what you can do is you can then calculate for the total crystal. You can then say for the total crystal, the total energy is 1/2 times the number of atoms times this sum that you can then calculate. And so if you minimize that, if you minimize this, then if you minimize this thing, you total with respect to R1, R2, R3, etc., then you get a crystal structure, because the crystal structure is just the shape, the R, the locations of the atom. The crystal structure is just whatever minimizes this total energy. The crystal structure minimizes that total energy. Let's make this look more. Okay, and so that's how you get the crystal structure of salt, for example. Similar, the same idea as before. So the last bonding one that we haven't talked about, the last one, the fourth type of bonding, is metallic bonding. And we'll do that next time, because I realize I've gone pretty significantly over. And so let's just stop here. So that's the end of this lecture, and we'll do metallic bonding next time. Okay, bye-bye.